Hello and welcome back. Let me open tonight with something that is true of you at this moment, lying still in the dark. You are moving at about 630 kilometers per second, not the Earth's spin, which is a few hundred meters per second, not our orbit around the Sun, which is 30 kilometers per second, not even the Sun's journey around the galaxy, which is 230. This is on top of all of that, the motion of our entire galaxy, and everything gravitationally attached to it through space. 630 kilometers per second is about 2.25 million kilometers an hour. Since this sentence began, you have traveled further than the distance from here to the moon, several times over. It is the fastest you will ever move, and you have been doing it your whole life without the faintest sensation. And here is the part that makes it strange. That motion has a direction. It points toward a particular patch of sky, in the southern constellations of Hydra and Centaurus, and that patch is one we cannot see through. Because it lies behind the disk of our own galaxy, from where we sit inside the Milky Way. Looking that way means looking through the thickest part of our own home, through billions of stars, and, far worse, through great lanes of dust that absorb visible light almost completely. Astronomers have a name for that region, and it's beautifully blunt. They call it the Zone of Avoidance. For most of the history of the subject, maps of the galaxies simply had a blank stripe running across them, where nobody could see anything at all. And somewhere in that blank stripe is whatever we are falling toward. Tonight, slowly, and with nothing for you to remember, we're going to look at what's behind it. Let's start with that hidden region, because it shaped the whole history of this question. Imagine the sky as a flattened oval map, the way world maps flatten the globe. Plot every galaxy anyone has catalogued, and you get a scatter of points covering most of the oval, dense in some regions, sparse in others, showing structure. Except for a band running right across the middle. In old maps, that band is empty, not sparsely populated, completely blank, with a hard edge on each side. That band is the plane of our own galaxy, projected onto the sky. It's where the Milky Way's disk lies from our vantage point inside it, and it's where the stars and gas and dust are concentrated. Historically, that blank region covered something like 20% of the sky, a fifth of everything, entirely unavailable to extragalactic astronomy. And it's not a random fifth, it's a continuous band, which means it can cut straight through any large structure and hide the middle of it. The name Zone of Avoidance dates back to the 19th century, when Richard Proctor and later Edwin Hubble noticed that the mysterious nebulae seemed to avoid the plane of the Milky Way. For a while, people wondered whether that was telling them something about the nebulae. It wasn't. It was telling them about the dust. Let's spend a chapter on the obstacle, because it's more absolute than people expect. The disk of our galaxy contains interstellar dust, tiny solid grains, mostly silicates and carbon compounds, smaller than a wavelength of visible light, condensed out of the material shed by dying stars. There isn't much of it. By mass, it's about 1% of the interstellar gas, and the gas itself is thin, but it's spread across enormous distances, and dust is extraordinarily effective at absorbing and scattering light. The effect is strongly wavelength dependent. Blue light is scattered far more than red, which is why stars seen through dust appear reddened, the same reason sunsets are red. And the shorter the wavelength, the worse it gets. Looking through the plane of the galaxy toward the center, the extinction can exceed 30 magnitudes in visible light. That's a factor of more than a million. A galaxy that would be plainly visible in a small telescope becomes undetectable to the largest one ever built. There's also confusion. Even where the dust thins, the sheer density of foreground stars makes it difficult to pick out faint fuzzy objects behind them. A distant galaxy looks like a smudge, so do 1,000 overlapping stars. So the zone of avoidance is not a matter of looking harder. In visible light, it's simply closed. Getting behind it required looking in entirely different kinds of light, and that took most of a century. Before we ask what's pulling, let's establish that we're moving at all, because the measurement is one of the most elegant in astronomy. The universe is filled with the leftover glow of its hot beginning. microwave radiation arriving from every direction, at about 2.7 degrees above absolute zero. We've discussed it on other nights. The light released when the universe became transparent, 380,000 years in. If we were perfectly at rest with respect to that radiation, it would be the same temperature in every direction, to within the tiny primordial variations. It isn't. One half of the sky is very slightly warmer, and the opposite half very slightly cooler, by a few thousandths of a degree, in a smooth pattern with one hot pole and one cold pole. That's a Doppler effect. We're moving through the radiation, so it's slightly blue shifted ahead of us and red shifted behind, and blue shifted light is slightly hotter. The pattern is called the dipole, and it's by far the largest feature in the microwave sky, about 100 times larger than the primordial variations. It was detected in the 1970s, using instruments flown on high-altitude aircraft, and it's now measured with exquisite precision by satellites. From its amplitude and direction, our velocity can be extracted directly. And it says about 370 kilometers per second in the direction of the constellation Leo, which is the Sun's motion. To get the galaxies and the local groups, you have to subtract the parts we already understand. Let's do that subtraction, slowly, because it's a nice piece of bookkeeping, and the result is tonight's central number. The Sun orbits the center of the Milky Way at about 230 kilometers per second, in a direction that changes slowly over the 230 million years it takes to complete a circuit. That's known well from studying the motions of stars and gas. The Milky Way itself moves within the local group, pulled mainly by Andromeda, which we're approaching at about 110 kilometers per second. Subtract those from the 370 measured against the microwave background, accounting for directions properly, and what's left is the motion of the local group as a whole. That comes out at about 620-630 kilometers per second, toward a point in the sky in the region of Hydra and Centaurus, at a galactic latitude low enough that it sits close to the plane, close to the zone of avoidance. That's the number. Our entire local collection of galaxies, us, Andromeda, Triangulum, and dozens of dwarfs, is moving as a unit at that speed relative to the frame in which the oldest light looks uniform. And motion like that requires a cause. Gravity is the only candidate at these scales, which means there must be a substantial concentration of mass somewhere in that direction, pulling. There's a term for that leftover motion, and it's worth a chapter because it underlies everything tonight. The universe is expanding, and that expansion carries galaxies apart. A galaxy's recession speed, on average, is proportional to its distance, the relationship Hubble found in 1929. But galaxies don't only move with the expansion. Each one also has a motion of its own, caused by the gravitational pull of everything around it, the nearby clusters, the filaments, the voids. That extra motion is called peculiar velocity, using peculiar in its older sense of belonging to that particular object. Peculiar velocities are typically a few hundred kilometers per second, sometimes over 1,000 in dense environments. Against the general expansion, which reaches thousands of kilometers per second at moderate distances, they're a small perturbation. But they're an enormously informative one, because they're caused by gravity, and gravity responds to all mass, visible or not. Peculiar velocities are a direct probe of how matter is distributed, including the dark matter that dominates. The difficulty is separating them from the expansion. When you measure a galaxy's redshift, you get the sum of both. To extract the peculiar motion, you need an independent measure of the distance, and then you compare. If the galaxy is receding faster than its distance implies, it has a peculiar motion away from us, slower, and it's moving toward us. So the whole subject depends on measuring distances to galaxies accurately, independently of redshift, and that is genuinely difficult, which is why this field developed as slowly as it did. Let's spend a chapter on that problem, because everything tonight rests on it. Redshift gives you a distance only if you assume pure expansion, which is exactly the assumption you're trying to test. So you need something else. The standard approach uses standard candles or standard rulers. Objects whose intrinsic brightness or size you know, so that how faint or small they appear tells you how far they are. For nearby galaxies, individual variable stars work, as Hubble showed. Further out, they're too faint to resolve. So astronomers found relationships that apply to whole galaxies. For spirals, there's the Tully-Fisher relation, discovered in 1977. The faster a spiral galaxy rotates, the more luminous it is, and the relationship is tight. Measure the rotation from the width of its radio emission line. Predict the true brightness. Compare with the apparent brightness, and you have a distance. For elliptical galaxies, which don't rotate in an organized way, there's an equivalent involving how fast their stars move randomly, combined with their size and surface brightness. The early version was called the d-sigma relation, and it was later refined into what's known as the fundamental plane. None of these is precise for an individual galaxy. Typical uncertainties are 15 or 20%. But average over many galaxies in a region, and the errors shrink, and a coherent pattern can emerge from the noise. That's the technique that found what we're discussing tonight. In the early 1980s, a group of 7 astronomers set out to do exactly that, on a large scale, and the story of what they found is the center of this subject. They were Alan Dressler, Sandra Faber, David Burstein, Roger Davies, Donald Lyndon Bell, Roberto Terlevich, and Gary Wegner, British and American, spread across several institutions, and they collaborated for years. The astronomical community nicknamed them the Seven Samurai, and the name stuck. Their original goal wasn't to find a great mass concentration. They wanted to use elliptical galaxies as distance indicators, and to map how galaxies move in order to measure the density of the universe. So they observed hundreds of elliptical galaxies across the sky, measuring the velocity dispersions and surface brightnesses needed for their distance method, over years of telescope time on several continents. And when they analyzed the resulting map of peculiar velocities, they found something none of them expected. The galaxies weren't moving randomly. Over an enormous region, hundreds of millions of light-years across, they were all streaming in roughly the same direction. Us, and everything around us, and galaxies far beyond us, all flowing together toward the same part of the sky. It was called large-scale streaming, and it was reported in a series of papers in 1987 and 1988, and it caused a considerable stir. The obvious interpretation was that something enormous lay in that direction, pulling everything toward it. The papers estimated the mass required, and it was large, something like 5 times 10 to the 16th solar masses, tens of thousands of times the mass of the Milky Way, concentrated in a region a few tens of millions of light-years across. And the direction pointed straight into the zone of avoidance. Whatever it was, it sat behind the dust of our own galaxy, in a region nobody could survey properly. Alan Dressler, in a book written a few years later, called it the Great Attractor, and the name entered the literature and the popular imagination immediately. It's an unusually evocative term for a scientific object, and it did a great deal to make the subject famous. It also did some harm, because the name suggests a thing, a single object, mysterious and hidden, exerting an inexplicable pull. That's not what anyone was proposing. The proposal was a large concentration of ordinary matter, clusters of galaxies, and the dark matter around them, in a region we couldn't see well. There's nothing exotic about it. A large mass pulls. We're falling toward it. The only mystery was where exactly it was and how much of it there was, because our own galaxy was in the way. That distinction matters for tonight, and I'll return to it. The Great Attractor is not an anomaly in physics. It's an ordinary structure in an awkward location. Let's pin down the location, since we'll be looking at it for the rest of the evening. The direction is in the southern sky, on the border of the constellations Norma, Triangulum Australe, and Centaurus, close to the plane of the Milky Way, at a galactic latitude of around 7 degrees, which is deep within the obscured band. The estimated distance has varied over the years, with figures between about 150 and 250 million light-years commonly quoted. The most frequently used value is around 220 million light-years. That's far. Light from there left before the first dinosaurs. But on cosmic scales, it's local. Well within the region we can survey. If only we could see through the dust. And at roughly that distance and direction sits a real catalogued object. A rich cluster of galaxies known as Abell 3627, usually called the Norma cluster. It was catalogued in the 1950s from photographic surveys, but was thought to be unremarkable, precisely because the dust dimmed it so much that its true richness was hidden, correct for the extinction, and it turns out to be one of the most massive clusters in the local universe, comparable to the famous Coma cluster. So there is something there. The question that occupied the following decades was whether it's enough. To answer that, astronomers had to find ways to see into the zone of avoidance, and the solutions are ingenious. The key insight is that dust blocks short wavelengths far more than long ones. So if you observe at longer wavelengths, the obscuration drops dramatically. Infrared works reasonably well. In the near-infrared, extinction is perhaps a tenth of what it is in visible light, which turns an impossible problem into a difficult one. Whole-sky infrared surveys, first from a satellite in the 1980s, then from ground-based surveys in the 1990s and 2000s, revealed galaxies that optical surveys had missed entirely. Radio works better still. At the 21 centimeter wavelength emitted by neutral hydrogen, dust is essentially transparent. A radio telescope can detect the hydrogen in a galaxy behind the entire thickness of our own galactic disk without difficulty. The limitation is that this only finds galaxies with substantial hydrogen, which means gas-rich spirals, and not the gas-poor ellipticals that dominate cluster cores. So it's a partial view, biased towards certain types. X-rays are the third route. Hot gas in galaxy clusters glows in X-rays, and X-rays pass through dust unimpeded. So an X-ray survey finds clusters directly, regardless of obscuration, which turned out to be the decisive method for mapping the mass in that region. Between them, those three approaches open the blank stripe. Not completely. The innermost few degrees remain very difficult, but enough to see what's there. Through the 1990s and 2000s, the region was surveyed by all three methods, and a picture emerged. There's a substantial concentration of galaxies in that direction, spanning a large region, a complex of clusters and groups, sometimes called the Hydra Centaurus supercluster, or the Centaurus Wall, with the Norma cluster near its densest point. The Norma cluster itself was confirmed as genuinely rich. Hundreds of galaxies, hot X-ray emitting gas, and a mass in the range of 10 to the 15th solar masses. A major cluster, previously underestimated because of the dust. Radio surveys found a wall or sheet of galaxies extending across the region, suggesting a filament of the cosmic web running roughly across our line of sight. So the answer to, is there something there? Was clearly yes. There's a large structure, and it's in the right place, and it had been substantially hidden. But when the mass was totaled, the answer to, is it enough, was less satisfying. The concentration in that region, as best it could be measured, accounted for perhaps a fraction of the observed flow, significant, but not all of it. Which meant that either a great deal of mass was still hidden, or something further away was contributing. And by the late 1990s, attention began shifting to a structure much further out, beyond the Great Attractor, in roughly the same direction but about 3 times further away, sits the largest concentration of mass in the nearby universe. It's called the Shapley supercluster, at a distance of around 650 million light-years. It contains dozens of rich galaxy clusters packed into a region a few hundred million light-years across, an unusually dense knot of the cosmic web. The total mass is difficult to pin down, but estimates run to 10 to the 17th solar masses or more, which is roughly an order of magnitude greater than the Great Attractor region. It's further away, so its pull on us is weaker per unit mass. Gravity falls off with the square of distance, but it's so much more massive that the contributions become comparable. Modern analyses suggest that something like a third to a half of our motion may be attributable to the Shapley region, with the Great Attractor complex contributing a comparable amount, and other structures making up the rest. So the picture shifted. Rather than a single hidden object pulling us, we have a chain. We're being drawn towards the Hydra Centaurus concentration, which is itself being drawn towards Shapley, which sits at the center of the largest local overdensity. And the flows partly add together because they point in similar directions. The supercluster is named after an astronomer we met on another night, and the naming has a history. Harlow Shapley, who argued in the Great Debate of 1920 that the spiral nebulae were nearby, and was wrong about that, was nonetheless one of the most important astronomers of his era. He established correctly that the Sun is not at the center of the Milky Way, using globular clusters to map the galaxy's true shape. In the 1930s, working at Harvard on photographic plates from a station in South Africa, he catalogued an unusual concentration of galaxies in the constellation Centaurus, far more than the surrounding fields, in a region he described as a cloud of galaxies. He had no way to know how far away it was or how significant. It was simply a noticeable clumping on a photographic plate. It sat largely unexamined for decades. Only in the 1980s and 90s, once redshifts could be measured in bulk and the scale established, did anyone realize that Shapley's cloud was the largest concentration of mass within 1 billion light-years. There's something I like about that. A patch on a photographic plate from the 1930s, noted and set aside, turning out 50 years later to be the dominant gravitational feature of our region of the universe, and named, belatedly, after the man who noticed it and moved on. By the 2000s, the technique had matured into something more ambitious than measuring a single direction. Instead of asking, which way are we moving? Astronomers began measuring peculiar velocities for thousands of galaxies across the sky, and reconstructing the whole three-dimensional flow field. That's a demanding program. Each galaxy needs a redshift, which is comparatively easy, and an independent distance, which is not. Collaborations spent years assembling catalogues, the largest containing tens of thousands of galaxies with measured distances. And once you have a flow field, you can do something clever. Gravity is what produces the flows, and gravity comes from mass. So you can work backwards. Given the observed velocities, reconstruct the distribution of mass that would produce them. That reconstruction includes dark matter automatically, because gravity doesn't distinguish. And crucially, it works even in the zone of avoidance, because the flow of galaxies you can see tells you about mass you can't. That's the elegant part of this whole subject. The obscured region is invisible directly, but its gravitational effect is written in the motions of everything around it, and those motions can be read. So the map of what's behind our galaxy has been assembled largely by watching how the galaxies elsewhere move. In 2014, a group led by Brent Tully published a map based on that approach, and gave our neighborhood a name. Their method was to take the reconstructed flow field and ask a simple question of every point. If you follow the flow, where do you end up? Galaxies that converge toward the same destination belong together. That's the same logic used to define a watershed on land. Two raindrops falling on opposite sides of a ridge end up in different rivers, and the boundary between them defines a catchment area, even though there's no wall or fence, just a difference in which way the ground slopes. Applying that to galaxy flows produces a structure with a definable boundary, the region within which everything is flowing toward a common center. Our region turned out to be about 520 million light-years across, containing roughly 100,000 large galaxies and a mass around 10 to the 17th solar masses. They named it Laniakea, from Hawaiian words meaning immeasurable heaven. And the focus of the flow, the point everything within it is converging toward, sits in the Great Attractor region, in the direction we've been discussing all evening. So we live near the outer edge of a vast catchment, and everything within it, including us, is draining slowly toward a low point behind the dust of our own galaxy. That definition deserves a chapter, because it's subtler than it sounds, and it changed how the term supercluster is used. Historically, superclusters were defined by eye, regions where clusters of galaxies appeared unusually concentrated. It was a description of appearance rather than a physical definition, and different astronomers drew the boundaries differently. The flow-based definition is physical. It doesn't ask how galaxies look, it asks how they move. And that gives a unique answer for any point. Either its flow converges toward this attractor or another one. But there's an important caveat. A watershed boundary on Earth is permanent because the ground doesn't move. A cosmic one isn't, because the universe is expanding and accelerating. Laniakea is not gravitationally bound. Its outer regions are being carried apart by dark energy faster than gravity can gather them. The flows are real, and they're happening now, but they will not complete. The structure will be pulled apart rather than assembled. So we're falling toward a destination that will recede from us before we arrive. The flow is genuine, the direction is measured, and the journey never finishes. Which is a strange thing to hold, and rather a peaceful one at this hour. A current in a river that is itself slowly evaporating. In 2017, a paper by Yehuda Hoffman and colleagues added a piece that had been missing, and it reframes the whole question. Their reasoning starts from something simple. Gravity is only attractive, but the relative effect of an underdense region is repulsive. Imagine a region of space with less matter than average, a void. Everything around it is pulled toward the surrounding denser regions rather than toward the void. So relative to the average, material moves away from the void as though it were pushing. That's not a new force. It's just what happens when you compare motion to the average in a lumpy universe. But it means voids contribute to flows as much as clusters do, and they've been comparatively neglected because they're difficult to map, being defined by an absence. Hoffman's team used the reconstructed flow field to look for such regions in the direction opposite to our motion, and found one, a large underdense region on the far side of the sky from the Great Attractor. They named it the Dipole Repeller, and their analysis suggested it contributes roughly as much to our motion as the attracting structures do, about half of the total, pushing from behind while Shapley and the Great Attractor pull from ahead. Let's sit with that idea for a chapter, because it's counterintuitive and rather lovely. We're not simply being pulled toward a great mass, we're also being pushed away from a great emptiness, or more precisely, we're being pulled toward everything except that emptiness, which produces a net motion away from it. The two effects point in nearly the same direction, roughly opposite each other on the sky, and they add. So the answer to what's pulling us is a large concentration of galaxies, a couple of 100 million light-years away, a much larger one, 400 million light-years beyond that, and a vast region of relative emptiness in the opposite direction, all contributing comparably. There isn't a single answer, and there was never going to be. Our motion is the sum of the gravitational influence of everything within a few 100 million light-years, weighted by mass and by distance, and that sum has contributions from many structures. The Great Attractor is the largest single nearby contributor, which is why it got the name and the attention. But it's a term for a region rather than an object, and the region is one term in a longer sum, which makes the popular framing, a mysterious hidden thing pulling us in, quite wrong in an interesting way. There's no thing. There's a landscape with hills and valleys of density, and we're rolling down the slope of it. That image deserves developing, because it's the accurate way to hold this subject. The universe is not uniformly filled with matter. It has structure at every scale: galaxies, groups, clusters, filaments connecting them, sheets, and enormous voids between. That arrangement, the cosmic web, grew from tiny density variations in the early universe, of about 1 part in 100,000, amplified by gravity over 13 billion years. Regions that started slightly denser pulled in more material and became denser still. Regions that started slightly thinner lost material to their surroundings and emptied out. So the present universe is a landscape of gravitational potential. Hills where matter is sparse, valleys where it's concentrated, and slopes in between. And everything moves downhill, not falling in the everyday sense, because there's no preferred direction in space, but drifting from lower density regions toward higher density ones, on top of the general expansion. Our galaxy sits on a slope. Downhill is toward the Hydra Centaurus concentration, and, beyond it, toward Shapley. Uphill is toward the underdense region on the opposite side. So the 630 kilometers per second is a drift down a very gentle gradient, in a landscape whose features are hundreds of millions of light years across, and which took 13 billion years to form. Let's take a chapter on how that landscape formed, because it links tonight's subject to the beginning of everything. The variations that seeded it are visible directly in the faint mottling of the microwave background, patches slightly warmer and cooler than average, at the level of 1 part in 100,000, imprinted when the universe was 380,000 years old. Those correspond to slight differences in density, and the leading explanation traces them to the first fraction of the first second, when quantum fluctuations were stretched to enormous scales by a brief period of rapid expansion. Then gravity worked on them for 13 billion years. Dark matter, unaffected by radiation pressure, began collapsing first and built the framework. Ordinary matter fell in afterwards and formed stars and galaxies inside the structures already prepared. The collapse happened along one axis first, forming sheets, then along a second, forming filaments, then along the third, forming knots, which is why the cosmic web has the shape it does, with clusters at the intersections of filaments. And the process is still running, though it's slowing. Dark energy has been pulling the largest structures apart for about 5 billion years, which means the web is close to its final form. So the slope we're drifting down was laid out in the first instant, developed for 13 billion years, and is now essentially finished. Our motion is the tail end of a very long process. There's a genuine open question in this area, and it deserves careful handling because it's been overstated in some accounts. The standard cosmological model predicts how large peculiar velocities should be, statistically, on various scales. Bigger structures produce larger flows, but the predicted amplitude falls as you average over larger and larger volumes. Several measurements of the bulk flow, the average motion of everything within a given radius, have come out somewhat larger than the standard prediction. Not enormously, and the significance varies between studies, but consistently on the high side in some analyses. If that's real, it suggests either that there's more structure on very large scales than the model expects, or that something in the model needs adjusting. There was also a stronger claim, made around 2008, of a very large coherent flow extending to great distances, sometimes called dark flow, which was interpreted by its proponents as possibly reflecting structures beyond our observable horizon. That claim has not held up well. Subsequent analyses using better data have generally not confirmed it, and the community broadly regards it as unsupported. The milder bulk flow tension is different. It's a modest discrepancy in ongoing work, taken seriously, with the most likely resolutions being measurement systematics or incomplete sky coverage. It's the kind of thing that gets resolved quietly over a decade. A chapter on why anyone funds this, because peculiar velocities turn out to be scientifically valuable. They're one of the few direct probes of how matter is distributed, including dark matter, on scales of hundreds of millions of light years. Most other methods measure light, and light traces only the ordinary matter. Gravity traces everything. They also measure how quickly structure is growing, which is sensitive to the nature of dark energy and to whether general relativity holds on cosmic scales. Different theories predict different growth rates, and flows are one way to distinguish them. And they matter for a very practical problem, measuring the expansion rate of the universe. If you measure a nearby galaxy's redshift and interpret it as pure expansion, you'll be wrong by whatever its peculiar velocity happens to be. Correcting for that requires knowing the flow field. That's relevant to the tension we've discussed on other nights. The persistent disagreement between local and early universe measurements of the expansion rate. Peculiar velocity corrections are one of the systematic effects that has to be handled carefully, and they've been examined closely as a possible source of the discrepancy. The general conclusion is that they don't explain it, but the checking matters, and the flow measurements are what make it possible. So the Great Attractor program is not a curiosity about a hidden object. It's a mapping exercise with several serious uses, one of which is knowing how fast the universe is expanding. The obvious question And the answer is a clean no, for a reason that has nothing to do with distance. We're moving toward the Great Attractor region at 630 kilometers per second. It's roughly 220 million light-years away. At that speed, a naive calculation gives an arrival time of about 100 billion years. But the space between us is also expanding, and the expansion is accelerating. At that distance, the expansion is carrying the region away from us faster than our peculiar motion carries us toward it. So the separation is increasing, not decreasing. We're moving toward it in the sense that our motion, relative to the average, points that way. But in absolute terms, the gap is widening and will continue to. The same is true for essentially everything outside our own gravitationally bound group. The Virgo cluster, the Great Attractor, Shapley, all receding, all permanently out of reach. What will actually happen is that our local group merges internally into a single galaxy over the coming tens of billions of years, and then sits isolated as everything else crosses the horizon. So the flow is real and measured and ongoing, and it is a journey that will never arrive, which is, I think, one of the gentler facts in cosmology. There's nothing to prepare for, nothing approaching, and nothing at the end of it. Let's step back and put the Great Attractor in its historical context, because it arrived during a decade when the whole picture of the universe's structure changed. Until the 1970s, most astronomers pictured galaxies as roughly randomly distributed, with some clustering, the way trees are scattered in a forest with occasional thickets. Then redshift surveys began. Measuring a galaxy's redshift gives its approximate distance, so with enough of them, you can build a three-dimensional map. The first serious attempts, in the late 70s and 80s, mapped thousands of galaxies. And the maps didn't look random at all. They showed sheets and filaments, with enormous empty regions between, voids, tens or hundreds of millions of light-years across, containing almost nothing. In 1989, a survey revealed a structure that became famous, a sheet of galaxies over 500 million light-years long, nicknamed the Great Wall. Nothing that large had been expected. Larger structures have been claimed since, walls and filaments extending over 1 billion light-years, though the significance of some has been debated. So the discovery of large-scale streaming in 1987 landed in the middle of a general realization that the universe is far lumpier, on far larger scales, than anyone had assumed. The Great Attractor was one piece of that shift. That raises a question with a real theoretical answer, and it's worth a chapter. The Standard Model predicts the limit. Structure grew from initial fluctuations, and those fluctuations had a particular pattern, roughly the same amplitude on all scales, with a slight tilt. Combined with the age of the universe and the rate at which gravity can gather material, that sets a maximum size for structures that have had time to form. The usual figure quoted is a few 100 million light-years, up to perhaps 1 billion for the largest coherent features. Beyond that, the universe should look statistically uniform. Any two enormous volumes should contain roughly the same amount of matter. That principle, that the universe is homogeneous and isotropic on large enough scales, is foundational. Nearly all of cosmology assumes it. Which is why occasional claims of structures spanning several billion light-years cause discomfort. Several have been reported based on concentrations of quasars or gamma-ray bursts, and each has been contested on statistical grounds, because the human eye and simple algorithms find patterns readily in random data. The current consensus is that the largest genuinely established structures sit at the scale the model predicts, and that the more extreme claims are probably artifacts of how the data were analyzed. But it's an active area, and the question of where uniformity sets in is not fully settled. Our own Laniakea, at 500 million light-years, is entirely comfortable within the expected range. Let's spend a chapter on the difficulties, because it explains why the answers have shifted so much over 40 years. The core problem is that peculiar velocities are small differences between large numbers. A galaxy's redshift might correspond to 5,000 kilometers per second of recession. Its peculiar motion might be 300, so you need the distance accurate to a few percent to extract it. and galaxy distance methods are typically good to 15 or 20%. That means individual measurements are nearly useless. Everything depends on averaging many galaxies, which requires enormous surveys, and on controlling systematic errors that don't average away. And there's a subtle statistical trap. Because we can only detect galaxies bright enough to see, and because errors scatter galaxies in both directions, a distance-limited sample is biased. You preferentially catch objects that scattered toward appearing closer or brighter. Correcting for that requires careful modeling, and getting it wrong produces spurious flows. That effect, named after the Swedish astronomer Gunnar Malmquist, has been the source of several disagreements in this field. Some early claims of very large flows were reduced substantially when the bias corrections were improved. There's also the calibration problem. Distance methods must be anchored to something, and errors in the anchor propagate into everything. So the field has a history of results that shifted as methods improved. Larger flows revised downward, distances revised, mass estimates revised. That's not a sign of unreliability. It's what careful work on a hard measurement looks like from the inside. The modern versions of that work are large collaborative catalogues, and they're worth a chapter because they represent decades of accumulated effort. The Cosmic Flows project has released successive catalogues over the past 15 years, each larger than the last. The early versions contained a few thousand galaxies with measured distances. The most recent contained tens of thousands, drawn from many methods combined and cross-calibrated. Each entry represents real observational work, a rotation width measured from radio observations, or a velocity dispersion from a spectrum, or a supernova light curve followed for weeks. And combining methods is essential, because each has different strengths. Tully-Fisher works for spirals, the fundamental plane for ellipticals, the tip of the red giant branch for nearby galaxies where individual stars can be resolved, surface brightness fluctuations for smooth ellipticals, and supernovae for the most distant. Cross-calibrating them, making sure a distance from one method matches a distance from another for the same galaxy, is painstaking and is where much of the systematic uncertainty lies. The result is a three-dimensional map of both where galaxies are and how they're moving, covering a region a few 100 million light-years across. That map is what Laniakea and the dipole repeller were derived from, and it's steadily improving. Let's return to the Zone of Avoidance and the surveys that opened it, because the radio work is elegant. Neutral hydrogen emits at 21 centimeters, and at that wavelength, the dust of our galaxy is essentially transparent. So a radio telescope can detect gas-rich galaxies behind the entire thickness of the disk. The difficulty is coverage. Radio telescopes traditionally see a small patch at a time, and surveying a fifth of the sky one patch at a time is slow. The solution was multi-beam receivers, instruments with many separate feeds at the telescope's focus, each looking at a slightly different point, so that a single pass covers a wide strip. A system installed at the Parkes telescope in Australia in the late 1990s had 13 beams, and it made large-scale surveys of the obscured sky feasible for the first time. Those surveys found hundreds of previously unknown galaxies behind the Milky Way and mapped structures crossing the zone, including parts of the Great Attractor complex. The limitation, as we noted, is that this only sees gas-rich galaxies. Cluster cores are full of gas-poor ellipticals, which are invisible to this method. So the radio maps show the filaments and outskirts well and underrepresent the densest regions. Newer arrays with far more beams are now surveying the same sky much faster and deeper, and the picture behind the disk is filling in steadily. In 2016, a team led by Renée Krahn-Korteweg, who has spent much of her career surveying the Zone of Avoidance, reported a large structure that had been entirely hidden. They called it the Vela supercluster, and it lies in the direction of the constellation Vela, at a distance of around 800 million light-years, straddling the galactic plane where obscuration is severe. It was found by measuring redshifts for thousands of galaxies in the region, using a spectrograph capable of observing many objects at once and finding a strong concentration at a common distance, the signature of a large structure. The full extent isn't known, precisely because the densest part sits where the dust is thickest. But it appears to be a major concentration, possibly comparable to Shapley, and it lies in roughly the direction of our motion, which means it may contribute to the flow, and that its previous absence from the accounting is one reason the sums didn't balance. That's a striking thing to consider, that as recently as a decade ago, a structure of that size in our own cosmic neighborhood was simply unknown, because our galaxy was in front of it. It's also a reminder that the answer to tonight's question is still being assembled. The map has genuine gaps, and things are still being found in them. Let's be precise about how much is still obscured, because the situation has improved enormously but isn't solved. In the near-infrared, the effective zone of avoidance has shrunk considerably. Surveys now reach through most of the band, and the truly opaque region is perhaps a few degrees wide rather than 20. In radio and X-ray, the obscuration is essentially irrelevant, though those methods have their own limitations in sensitivity and in what kinds of objects they find. What remains difficult is the innermost region, within a few degrees of the galactic plane, and particularly toward the galactic center, where both the dust and the density of foreground stars are extreme. That's a narrow strip, but it runs across the whole sky, and it can still bisect a structure and hide its core. The practical consequence is that the mass distribution in the Great Attractor region is known less precisely than elsewhere. Estimates of how much is there carry larger uncertainties, and the possibility of an additional undiscovered concentration hasn't been eliminated. So when someone says the Great Attractor is hidden, that's now only partly true. We know a great deal about the region. We know less about it than about equivalent regions elsewhere in the sky. And the difference matters when you're trying to balance a gravitational budget. Since voids matter as much as clusters, let's look at the one on our doorstep. There's a large, underdense region immediately adjacent to our local group, extending away from us in the direction of the constellation Aquila. It's called the local void, and it's remarkably empty, containing far fewer galaxies than an average region of its size. Its extent is estimated at over 150 million light-years across, and it begins essentially at the edge of our own neighborhood. And it's pushing us, or more precisely, we're being pulled away from it by everything on the other side, which produces a net motion away from the void. Analyses of the local flow field suggest this contributes substantially to our motion, comparable to the pull from Virgo, and in a broadly consistent direction with the larger flow toward Hydra Centaurus. There's also evidence that the void is expanding faster than average, as material drains out of it into the surrounding structures, which increases the effect over time. So one of the more significant contributors to our 630 kilometers per second is a large amount of nothing, sitting right next to us, that we're drifting away from. Before the Great Attractor was known, the accepted explanation for our motion was something closer, and it's still part of the answer. The Virgo cluster is the nearest large cluster of galaxies, about 55 million light-years away, containing over 1,000 galaxies, dominated by a giant elliptical at its center. Our local group is falling toward it, at a speed usually estimated at a couple of 100 kilometers per second. That's called Virgo-centric infall, and it was the first component of our peculiar motion to be identified in the 1970s. Virgo is the center of what used to be called the local supercluster, a flattened structure of galaxies and groups extending across 100 million light-years or so, of which we're an outlying member. Gerard de Vaucouleurs argued for its existence from the 1950s against considerable skepticism. Under the modern flow-based definition, the local supercluster is not a separate structure, but a component of Laniakea, a substructure within the larger catchment. So the sequence is, we fall toward Virgo, and the whole Virgo region falls toward the Great Attractor complex, and that falls toward Shapley. Each level of structure is drifting toward the next one up, and all of those motions add together into the single number measured against the microwave background. Let's assemble the full address, from small to large, because it's satisfying to have in order. You're on a planet orbiting a fairly ordinary star, about 26,000 light-years from the center of the Milky Way, in a minor spiral structure between two major arms. The Milky Way is one of two large galaxies in the local group, along with Andromeda and about 80 smaller companions, spread across roughly 10 million light-years. The local group sits within a flattened structure of nearby galaxies, sometimes called the local sheet, and is an outlying member of the concentration around the Virgo cluster. That whole region belongs to Laniakea, the catchment of about 100,000 large galaxies, 520 million light-years across, all flowing toward the Great Attractor region in Norma. And Laniakea is adjacent to other such catchments: the Perseus-Pisces supercluster on one side, the Coma region, and beyond them others. Laniakea itself appears to be flowing toward the Shapley concentration, which may make it part of an even larger basin. That's the address. And notice that at every level above the local group, the structure isn't bound. It's a flow pattern rather than an object, and dark energy will pull it apart before it ever assembles. So the honest version of our cosmic address ends at the local group. Everything larger is a description of a current, not a place. A short chapter on the naming, because it's a nice story. When Brent Tully's team defined the structure in 2014, they needed a name, and they asked a Hawaiian language expert at a Honolulu community college, Navar Napoleon, for a suggestion. He proposed Laniakea, from Lani meaning heaven and Akea meaning spacious or immeasurable heaven. The naming was also intended to honor the Polynesian navigators who crossed the Pacific using the stars, over enormous distances, with no instruments, reading swells, birds, and the positions of rising and setting stars. There's an appropriateness in that. Those navigators worked out their position on a featureless ocean by careful observation of motion and direction, which is precisely what the Laniakea map does at a different scale, establishing where we are by measuring how everything moves. Much of the observational work also came from telescopes on Hawaiian mountains, which adds a further connection. Scientific names are usually dull and functional. This one isn't, and it's now in the standard literature, which means a Hawaiian phrase for immeasurable heaven is the formal designation for the region of the universe we live in. There's a technical question that has occupied this field for decades, and it has a satisfying framing. How far do you have to go before the pulls balance out? Here's the idea. If you sum the gravitational effect of all the mass within some radius of us, you get a predicted velocity. Do that for progressively larger radii, and the prediction should eventually stop changing, because beyond a certain scale, the universe is uniform, and a uniform distribution pulls equally in all directions and produces no net effect. The distance at which the prediction stops changing is called the convergence depth, and finding it tells you which structures actually matter. Early work suggested convergence within about 200 million light-years, which pointed to the Great Attractor region as the dominant cause. Later analyses, using deeper surveys, found that the prediction kept growing beyond that, implicating Shapley at 650 million light-years. Current estimates generally suggest that most of our motion is generated within about 500 million light-years, with a substantial tail extending further. That's a meaningful result. It says the answer to tonight's question isn't a single object at a single distance, but an accumulation. The Great Attractor region contributing, Shapley contributing, the local void contributing, and smaller structures adding smaller amounts. There's a class of simulation designed specifically for this problem, and it's rather clever. Ordinary cosmological simulations start with random initial conditions matching the statistical properties of the early universe, and produce a universe that looks like ours statistically, but doesn't match it in detail. Different galaxies in different places. Constrained simulations do something else. They take the observed distribution and motions of galaxies in our actual neighborhood, work backwards to figure out what initial conditions would produce them, and then run those forward. The result is a simulated universe that contains our actual structures, a Virgo cluster in the right place, a local group, a Great Attractor region, evolved with full physics. That lets researchers ask questions the observations can't answer directly. What's the total mass distribution? including the parts we can't see? What will the flows do over the next billions of years? How much of the zone of avoidance is filled in? Several such projects have run over the past 2 decades, with successively better data. The most recent produced local universes that reproduce the observed flow field closely. And they're used, among other things, to estimate what's hidden. If the simulation reproduces all the visible structure and the observed motions, then whatever mass it places in the obscured region is a reasonable guess at what's actually there. Here's an application of flow measurements that goes beyond mapping, and it's one of the reasons the field is well funded. Peculiar velocities are produced by gravity acting on density variations. So if you can measure both the density field from galaxy surveys and the velocity field independently, you can check whether they're consistent with the theory of gravity you're using. General relativity makes a specific prediction for the relationship. Given a certain amount of clustering, structure should grow at a particular rate, producing particular velocities. Modified theories of gravity, proposed as alternatives to dark energy, generally predict different growth rates. Some make structure grow faster, some slower. So comparing the observed flows to the observed clustering is a direct test, on scales of hundreds of millions of light years, far beyond anything testable in the solar system or in binary pulsars. So far the results are consistent with general relativity, with the precision improving as catalogues grow. That's another line of evidence against most modified gravity proposals, complementing the tests from gravitational waves and from the microwave background. And it means our own 630 kilometers per second is a data point in an ongoing test of whether Einstein's theory holds across the largest scales anyone can measure. There's a subtlety about the microwave dipole that has become interesting recently, and it deserves an honest chapter. The standard interpretation is that the dipole is entirely kinematic, caused by our motion, full stop. That's the assumption underlying every number I've given tonight. But there's a way to check it. If the dipole is due to our motion, then the same motion should produce a matching dipole in the distribution of distant objects. Because sources ahead of us appear slightly brighter and slightly more numerous, and those behind appear slightly fainter. That effect is predictable in size, and it's been looked for in catalogues of distant radio galaxies and quasars. Several studies have found a dipole in those catalogues that points in roughly the right direction, but is larger than the microwave dipole predicts, in some analyses by a factor of 2 or more. If that holds up, it would mean either that the microwave dipole isn't entirely kinematic, or that the distant universe isn't as uniform as assumed, both of which would be significant. The measurements are difficult, with real systematic concerns about how catalogues are assembled and how sky coverage affects the result, and not everyone is convinced. It's an unresolved anomaly rather than an established finding, and it's being actively examined with better data. I mention it because tonight's central number rests on an assumption that is, at the moment, being tested and found slightly uncomfortable. Let's spend a chapter on the framing, because this subject is presented misleadingly more often than almost any other in astronomy. The Great Attractor is routinely described as a mysterious force, an unexplained anomaly, something pulling us toward an unknown fate. None of that is accurate. What it actually is, a large concentration of galaxies and dark matter, of an entirely ordinary kind, at a measured distance, in a direction that happens to be behind our own galaxy's dust. There is no unknown physics involved. Gravity attracts mass. A lot of mass is over there. We're drifting that way. The only genuine difficulty was observational. A fifth of the sky was hard to survey, so the accounting took decades, and that difficulty has been substantially resolved. The remaining open questions are quantitative rather than conceptual. Exactly how much mass is in the region? What fraction of our motion comes from? Where? Does the sum converge, and at what distance? Those are ordinary scientific questions, with ordinary answers being refined by ordinary methods. I labor the point because the dramatic framing produces a particular kind of unease, the sense of being dragged towards something unknown. And the accurate version is the opposite. We're drifting gently down a well-mapped gradient toward a place we'll never reach, at a speed that has no effect on anything. Nothing. That's the whole answer, and it's worth a chapter on why. You feel acceleration, not velocity. Sitting in a smoothly moving vehicle at constant speed on a straight road, you feel nothing. The sensation comes only from changes, turning, braking, accelerating. And our motion through the universe is essentially unaccelerated on any timescale that matters. The gravitational pull producing it is extraordinarily gentle, spread over hundreds of millions of light years. It changes our velocity by a few kilometers per second over millions of years. There's also no medium to feel. Space isn't a substance you move through. There's no wind, no resistance, no friction. Moving at 630 kilometers per second through space is physically identical to being at rest, as far as any local experiment can determine. The only reason we can measure it at all is the microwave background, an external reference that happens to fill the universe and to have been left behind at a moment when everything was nearly at rest relative to it. So the 630 kilometers per second is real and measured and has no local consequences whatsoever. It doesn't shorten anything or heat anything or push on anything. You've been traveling at that speed your entire life, along with the entire galaxy, and it has never once affected a single thing about your day. Since we've been adding motions all evening, let's put them together properly, because the stacking is enjoyable. The Earth spins, carrying someone at the equator at about 460 meters per second, and less at higher latitudes. The Earth orbits the Sun at about 30 kilometers per second, completing a circuit each year. The Sun orbits the galactic center at about 230 kilometers per second, taking around 230 million years for one lap. The Milky Way moves within the local group, mainly toward Andromeda, at around 110, and the local group as a whole moves at about 630 relative to the microwave background, toward Hydra Centaurus. Those don't simply add, because they point in different directions and change over time. The net result, for the Sun, is the 370 kilometers per second toward Leo that the dipole measures. So at any instant, you're participating in 5 nested motions, on timescales from a day to hundreds of millions of years, with the largest of them the one nobody can feel, and nobody suspected until the 1970s. And all of it proceeds while you lie perfectly still. Let's spend a chapter describing what these maps actually look like, because they're beautiful objects and worth picturing. Imagine a 3-dimensional volume, a few hundred million light years across, with our galaxy near the middle. Scattered through it are dots, the observed galaxies, denser in some regions, sparse in others, strung along filaments. Now add arrows, for each region, the direction and speed of the flow. And instead of individual arrows, draw streamlines, continuous curves following the flow, the way a diagram of wind or water currents does. What emerges looks strikingly like a river system. Streamlines converge along filaments, gathering into larger channels, and all of them run toward a common low point. Void regions show streamlines diverging, flowing outward toward the surrounding walls. The published visualizations of Laniakea use exactly that presentation, and the effect is immediate. A great basin, with tributaries feeding in from every side, and our own position out near the rim. There's a specific detail I like. In those maps, we sit close to the boundary, the ridge separating our catchment from the neighboring one. Shift our position slightly, and we'd belong to a different supercluster entirely. Which is a curiously arbitrary thing to learn about your address. That you live near the edge of the watershed, and that the assignment could have gone either way. Let's take a chapter to name what's actually over there, since we've been vague about it. The Norma cluster, Abell 3627, sits closest to the flow's focus, a rich cluster of hundreds of galaxies, with hot X-ray gas and a mass around 10 to the 15th solar masses. It's the single most massive concentration in the immediate Great Attractor region. Nearby, in the same complex, is the Centaurus cluster, well studied, somewhat closer to us, with a bright central galaxy and a well-mapped X-ray halo. The Hydra cluster lies in the same general direction, at a comparable distance, and is another substantial member. together with numerous smaller groups and a wall of galaxies connecting them. These form the Hydra Centaurus complex, the local overdensity that the flow points towards. For comparison, the Coma cluster, which is the standard example of a rich cluster and sits in a different part of the sky, has a mass of a few times 10 to the 15th solar masses. So the individual clusters in the Great Attractor region are comparable to Coma, and it's their combined presence, plus their position relative to the surrounding voids, that produces the effect. None of them is exotic. They're ordinary clusters, the sort that appear in catalogues everywhere, that happen to sit in the awkward part of the sky. For symmetry, let's look at what lies in the opposite direction, because it completes the picture. Roughly opposite the Great Attractor on the sky sits the Perseus-Pisces supercluster, a long chain of clusters and groups, one of the more prominent structures in the northern sky, at a distance of around 250 million light-years. It's a substantial concentration, and it pulls on us in the opposite direction to the Great Attractor complex, reducing the net motion rather than adding to it. The fact that our motion points toward Hydra Centaurus, despite Perseus-Pisces pulling the other way, means the Hydra Centaurus side, plus Shapley beyond it, plus the void on the Perseus side, wins the tug-of-war. That's how these sums work. Every structure in the universe pulls on us. Nearly all of the effects cancel, because for every mass in one direction, there's usually a comparable one in the opposite, and what's left over is the small residual imbalance. 630 kilometers per second is that residual. It's what remains after the enormous majority of the gravitational influences on us have cancelled each other out, which is worth sitting with. The largest motion you'll ever have is a rounding error in a sum where nearly everything else cancelled. Let's follow the flow forward in time, because its future is not what you'd expect. Today, galaxies within Laniakea are drifting toward its focus, and material continues to fall into clusters and filaments. Structure is still growing, in the sense that dense regions are still becoming denser relative to average. But dark energy has been accelerating the expansion for about 5 billion years, and its effect grows as matter thins out. Increasingly, the expansion overwhelms the flows. So over the coming billions of years, the streaming will slow and stop. Regions that are currently falling toward the Great Attractor will instead recede from it, carried apart faster than gravity can gather them. Only bound structures survive, individual clusters and small groups like ours. Everything larger is pulled apart. The Laniakea flow pattern, in other words, is a snapshot of a process that is already close to its end. It will not complete. The Great Basin will never fill. The water will evaporate from the valley before it reaches the bottom. So we are drifting toward a destination that is receding, in a current that is failing, in a structure that will never assemble, which is either poignant or peaceful, depending on the hour. And at this hour, I'd suggest peaceful. For contrast, let's be clear about what does survive, because it's not nothing. Our local group is genuinely bound. Its members are held by mutual gravity, and the expansion has no effect within it. It will not be pulled apart. Instead, it will merge. Andromeda and the Milky Way will interact over the coming billions of years, and the smaller galaxies will spiral in, and eventually the whole group becomes a single large elliptical galaxy. That object will then sit isolated, as everything else. Virgo, the Great Attractor, Shapley, all of it, crosses beyond the horizon and disappears from view. Estimates put the full isolation somewhere between 100 billion and a few hundred billion years from now. At which point, our merged galaxy would be, for practical purposes, the entire observable universe from the inside. An observer then would see local stars and nothing beyond, with no way to discover that anything else had ever existed. So the flow we've spent the evening on has a definite end. It stops, reverses in effect, and everything we're currently drifting toward becomes permanently unreachable and then invisible. And the only thing that persists from tonight's picture is the small bound group we belong to, condensed into a single object in an empty sky. Before the Seven Samurai, someone else reported large-scale streaming, and the reception she got is part of this story. In the mid-1970s, Vera Rubin, who we've discussed on other nights for her work on galaxy rotation and dark matter, collaborated with Kent Ford and others on a study of distant spiral galaxies. They found evidence that our galaxy appeared to be moving relative to those distant galaxies at a few hundred kilometers per second, in a direction that didn't match the expectations of the time. The result was published in 1976 and became known as the Rubin-Ford effect, and it was received with considerable skepticism. The sample was small, the distance indicators were questioned, and several astronomers argued the effect was an artifact of selection. Rubin later described the episode as bruising and moved on to other work, the rotation curves that made her famous. Then, a decade later, the microwave dipole was measured properly, and the Seven Samurai found large-scale streaming, and it turned out that a substantial peculiar motion of our galaxy was real after all. The details of the original claim didn't hold up in every particular, and the direction and magnitude were revised. But the basic assertion that we're moving substantially relative to distant galaxies was correct, and it had been reported and largely dismissed years earlier. Alan Dressler wrote about the Seven Samurai's work afterwards, and the account is worth a chapter because it conveys something about how discoveries actually happen. The group had spent years on observations on several continents, in an era when telescope time meant traveling to a mountain, staying for a week, and hoping for clear skies. They accumulated data slowly and analyzed it collectively, arguing over methods. The streaming result wasn't a moment of revelation. It emerged from the analysis as a pattern that wouldn't go away, a systematic residual that persisted through every attempt to remove it. And their first reaction, by his account, was suspicion of their own work. A coherent flow across the whole survey volume is exactly what a systematic error would look like. So they spent a long time trying to find the mistake. Only when the alternatives had been eliminated did they publish, and even then, with appropriate caution. The community's response was mixed, considerable interest and considerable doubt, with some groups reporting smaller flows. That process, years of data, suspicion of your own result, elimination of alternatives, cautious publication, and then a decade of argument, is what a significant discovery in observational cosmology actually looks like. It's much slower and much less dramatic than the popular version, and considerably more admirable. Something worth stating plainly. The estimated mass of the Great Attractor has been revised downwards substantially over the decades. The original 1988 estimate was around 5 × 10⁻XVI solar masses concentrated in the region. Later work, using better distance indicators and better bias corrections, reduced both the inferred flow amplitude and the required mass. Modern estimates for the mass concentration in the Hydra Centaurus region are considerably lower, perhaps a few times 10⁻¹5 solar masses for the identified clusters, with additional mass in the surrounding structures. At the same time, the recognition of Shapley's contribution, and later of the void on the opposite side, meant less of the flow needed to be explained by the nearby structure, so the picture went from one dominant hidden mass to a distributed set of contributions, none individually sufficient. That's a substantial change in the answer over 35 years, and it's worth being clear about, because popular accounts often still quote the original 1,988 numbers as though they were current. And it's a good illustration of how this works. Nobody was wrong in a culpable sense. The early estimates were the honest output of the methods available. Better methods gave different numbers. The picture reorganized. That's the process functioning correctly. Let's spend a chapter on the surveys that gave us the density field, because they're one of the great collective achievements of modern astronomy. The first systematic redshift survey of any size was carried out at the Center for Astrophysics in the 1980s, measuring redshifts for a few thousand galaxies and producing the first genuine three-dimensional maps. Those maps revealed the structure we've discussed: sheets, filaments, and voids. One of the famous early slices showed a stick-figure pattern of galaxies with enormous empty regions, which was startling at the time. Then came larger surveys. A survey in Australia measured over 200,000 redshifts around the turn of the century, and the Sloan Digital Sky Survey, operating from New Mexico from 2000 onwards, eventually measured millions. Those surveys transformed the field. With millions of galaxies mapped in 3 dimensions, the statistical properties of the cosmic web could be measured precisely and compared to simulations. They also provide the density field that peculiar velocity work needs. If you know where the galaxies are, you can predict the gravitational field they produce and compare that prediction to the observed flows. The comparison works well. The predicted and observed velocity fields agree within the uncertainties, which is a substantial success for the standard model, and one of the reasons nobody considers the Great Attractor mysterious in a physics sense. Let's picture the structure those surveys revealed, because it's genuinely beautiful, and it's what we're moving through. At the largest scales, matter is arranged in a network. Long filaments, threads of galaxies, hundreds of millions of light years in length, meet at dense knots where clusters sit. Between the filaments are sheets, flattened walls of galaxies, and between everything are voids, enormous, nearly empty bubbles, tens or hundreds of millions of light years across. Most of the volume of the universe is void. Most of the mass is in the filaments and knots, which occupy a small fraction of the space. The visual comparisons people reach for are foam, or a sponge, or a neural network, or the fine structure inside a piece of bread. All of them capture something. And the arrangement emerged from gravity acting on tiny initial fluctuations, exactly as simulations produce when you run the physics forward from the observed starting conditions. That agreement between what the simulations produce and what the surveys find is one of the strongest pieces of evidence for the whole cosmological picture. Our own galaxy sits in a modest filament, near the edge of a large basin, adjacent to a substantial void, which is a fairly typical location. Most galaxies live in filaments and sheets rather than in clusters or voids. Since voids do half the work in our story, let's spend a chapter on them. A typical void is perhaps 100 million light-years across and contains a small fraction of the average density, not empty but sparse, with a scattering of small galaxies rather than the groups and clusters found elsewhere. The galaxies that do live in voids are interesting. They tend to be small, blue, gas-rich, and still forming stars, because they've never been stripped by a dense environment or had their gas heated by a cluster. The largest known voids are enormous. One in the direction of Botez, discovered in 1981, is around 300 million light-years across and contains far fewer galaxies than it should. Its discovery was a shock at the time. There's also an unusually large underdense region in the direction of the microwave background's cold spot, which some have proposed as a partial explanation for that anomaly, though the connection is debated. Voids matter for cosmology because their sizes and shapes depend on the expansion history and on the nature of dark energy, and because they're comparatively simple, with less matter, the physics is less complicated by the messy processes that dominate in dense regions. And as we've discussed, they push, which is why the dipole repeller, a region defined by an absence, turns out to be one of the main answers to tonight's question. Let's return one more time to the zone of avoidance, because the work continues and it's improving quickly. New radio arrays, with dozens of beams and wide fields of view, are surveying the southern sky for neutral hydrogen far faster than the previous generation. Those surveys will detect tens of thousands of galaxies behind the galactic plane. Optical and infrared surveys are pushing deeper, with better modeling of the extinction, so that galaxies can be recovered from regions previously considered hopeless. X-ray surveys from orbit continue to find clusters regardless of dust, and a recent all-sky X-ray survey has catalogued enormous numbers of them, including in the obscured band. And a new generation of spectroscopic instruments, capable of measuring thousands of redshifts simultaneously, is being used to map the structures found by those surveys in 3 dimensions. Within a decade or two, the zone of avoidance should be substantially mapped, at least outside the innermost few degrees. The gravitational budget should then close much more convincingly, and the relative contributions of each structure should be known. which means tonight's answer is provisional in a specific way. Not wrong, but incomplete. And due to be completed by people currently pointing telescopes at a part of the sky that used to be blank on every map, let's spend a chapter on the microwave background as a reference, because there's a subtlety that's easy to misunderstand. Relativity says there's no absolute rest, no preferred frame against which all motion can be measured. That's foundational, and it's been confirmed exhaustively. So how can we say we're moving at 630 kilometers per second? The answer is that the microwave background provides a preferred frame without being an absolute one. It's the frame in which that radiation appears uniform. And because the radiation was released everywhere at once when matter was nearly at rest relative to itself, that frame is the same, to good approximation, everywhere in the universe. It's the frame in which the universe as a whole looks isotropic, not a violation of relativity, because it's defined by the contents of the universe rather than by space itself. The laws of physics are still the same in every frame. It's just that one frame happens to be picked out by what's in it. The analogy sometimes used is a room full of still air. There's no absolute rest, but there's an obvious frame, the one in which the air isn't moving, and you can meaningfully say you're walking at a certain speed relative to it. So our motion is real and measurable, and it's motion relative to the average matter of the universe, and that's the only sense in which the number means anything, which is quite enough for it to be interesting. A related thought, since we've been discussing motion for 2 hours. The constellations are temporary. Every star you can see is moving relative to us, typically at tens of kilometers per second, and the patterns are accidents of the present moment. The stars in a given constellation are usually unrelated, sitting at wildly different distances, moving in different directions, appearing near each other only from this vantage point. Over tens of thousands of years, the patterns visibly distort. Over 1 million, they dissolve entirely. Every named figure in the sky, in every culture that has ever named them, is a passing arrangement. The same is true at every scale. The galaxies in our group are moving toward each other. The groups within Laniakea flowing toward its focus. Laniakea itself is drifting toward Shapley, and all of it is superimposed on the general expansion. So the still sky above your house is not a fixed backdrop. It's a snapshot of an enormously complicated set of motions, none of them perceptible on any human timescale, all of them proceeding tonight exactly as they have for billions of years. And the most striking of them, the fastest, the one that involves everything you have ever seen moving together, is the one nobody suspected until 50 years ago, and which points at a part of the sky we can't look at. Since our motion is measured against the assumption that the universe is uniform on large scales, let's spend a chapter on that assumption. It's called the cosmological principle. The universe is homogeneous, the same everywhere, and isotropic, the same in every direction, when averaged over sufficiently large volumes. It's not obviously true. Locally, the universe is plainly lumpy, galaxies, clusters, voids. The claim is only that, if you average over volumes of 1 billion light years or so, the lumps even out. The evidence is reasonably good. The microwave background is uniform to 1 part in 100,000 once the dipole is removed. Galaxy counts in different directions agree. Once you correct for obscuration, the distribution of distant radio sources and quasars is close to uniform. And it's essential. Nearly all of cosmology assumes it, because without it, the equations describing the universe's expansion don't apply in their usual form. The anomalies we've mentioned, the quasar dipole, the occasional very large structure claims, the bulk flow tension, are all in effect tests of this principle. Each is currently unresolved, and none is decisive. Most cosmologists expect the principle to hold, and the anomalies to be resolved as systematics. But it's worth knowing that the foundation is being probed rather than assumed unexamined, and that a genuine violation will be one of the biggest results in the field. Let me put 630 kilometers per second into a few comparisons, slowly, because the scale is hard to hold. It's about 2.25 million kilometers per hour. In a day, we travel about 54 million kilometers. a bit more than a third of the distance from the Earth to the Sun. In a year, we cover roughly 20 billion kilometers, around 4 times the distance to Neptune. In a human lifetime, about 1.5 trillion kilometers, a sixth of a light year, which is a substantial fraction of the way to the nearest star. And yet it's slow by cosmic standards. It's a fifth of 1% of the speed of light. At that speed, crossing the distance to the Great Attractor region would take 100 billion years, which is longer than the universe has existed by a factor of 7. And, as we've discussed, the gap is widening anyway. So the fastest motion you'll ever have is simultaneously enormous by human standards and negligible by cosmic ones. Fast enough to cross the solar system in a few days, slow enough that it will never take us anywhere. Something worth noting about tonight's subject: essentially nothing in it was observed directly. Nobody has seen the Great Attractor as an object. What was observed was a temperature difference of a few thousandths of a degree across the microwave sky, the widths of radio emission lines from hundreds of spiral galaxies, the velocity dispersions of hundreds of ellipticals, X-ray emission from hot gas. From those, distances were inferred. From distances and redshifts, peculiar velocities were inferred. From peculiar velocities, a flow field was reconstructed. From the flow field, a mass distribution was inferred, including in regions nobody can see. Each step involves modeling and assumptions, and each carries uncertainties that had to be propagated through. And the result is a 3-dimensional map of the mass in a region hundreds of millions of light years across, most of which is invisible dark matter, much of it behind an opaque screen. That's a remarkable thing to have accomplished, and it's worth appreciating the indirectness. We know what's behind our own galaxy, largely because we watched how everything else moves. Which is, when you think about it, the same technique a person uses to detect something behind them in a dark room, not by seeing it, but by noticing how everything else responds. Let's be honest about the gaps, because several remain. We don't know precisely how much mass is in the Great Attractor region, because the innermost part of the Zone of Avoidance is still poorly surveyed, and cluster masses are hard to measure. We don't know exactly how the total motion divides between contributors. Estimates of Shapley's share, the Great Attractor's share, and the void share vary between analyses. We don't know whether the sum converges within the surveyed volume, or whether structures further out contribute meaningfully. We don't know whether the bulk flow measurements that come out slightly high are revealing something or reflecting systematics. And we don't know why the dipole in distant quasar catalogues appears larger than the microwave dipole, predicts an anomaly that, if confirmed, would touch the foundations. What we do know is solid. We're moving at a well-measured speed in a well-measured direction. The cause is gravitational. The structures responsible have been identified, and there is no unknown physics involved. So the remaining questions are quantitative, and they're being answered by surveys currently underway, which is a rather satisfying position for a subject that began with an unexplained anomaly and a blank stripe on a map. Let me offer a thought experiment, because it's a pleasant thing to picture. Suppose, for one night, the dust and stars of our own galaxy became transparent, that you could see through the disk as easily as through empty space. The band of the Milky Way would vanish from the sky, and in its place, in the direction of Hydra and Centaurus, you'd see what has been behind it all along. A concentration of galaxies, thousands of them, spread across a substantial patch of sky. They'd be faint, of course. At 200 million light years, even a rich cluster is a scattering of dim smudges rather than anything dramatic. You'd need a telescope to see them properly, and the Norma cluster would look much like the Coma cluster does in photographs. But the direction would be visible. There'd be something to point at, in the region where we currently point at nothing. And the strange thing is, how ordinary it would look. Not a maw, not a vortex, not anything that suggests a great pull. Just a somewhat richer patch of galaxies in one part of the sky, indistinguishable at a glance from the equivalent patches we can already see elsewhere. That's the honest picture. The reason it has a dramatic name is entirely because we can't see it, And if we could, it would have been catalogued as an ordinary supercluster in the 1950s, and nobody would have made a fuss. Since everything depends on how much mass is over there, let's spend a chapter on how a cluster's mass is measured. There are three main methods, and their agreement is what gives confidence. The first uses motion. Measure the velocities of the member galaxies, and the spread tells you how deep the gravitational well must be to hold them. That's what Zwicky did with Coma in 1933, and it's how dark matter was first inferred. The second uses hot gas. Clusters are filled with gas at tens of millions of degrees, glowing in X-rays. That gas is held in place by gravity, and its temperature and distribution reveal the mass required, a completely different physical argument from the first. The third uses gravitational lensing. A cluster's mass bends the light of galaxies behind it, distorting their images. Measure the distortion, and you can map the mass directly, without assuming anything about what it's made of, or whether it's in equilibrium. For well-studied clusters, the three agree reasonably well, typically giving masses where most of the total is dark matter, a factor of 5 or more beyond the visible galaxies and gas combined. For the clusters in the zone of avoidance, the X-ray method works best, because X-rays pass through dust, which is why the confirmation that the Norma cluster is genuinely massive came largely from X-ray satellites. There's a fourth technique worth its own chapter, because it works regardless of distance or obscuration, and it's beautifully indirect. When the microwave background passes through a galaxy cluster, some of its photons collide with the fast-moving electrons in the hot intracluster gas and pick up energy. That shifts the spectrum slightly. Fewer low-energy photons, more high-energy ones. The result is that a cluster leaves a small imprint on the microwave sky, a shadow at some frequencies and a slight excess at others, at a precisely predictable pattern. It's called the Sunyaev-Zeldovich effect, after the two Soviet physicists who worked it out in the late 1960s. Its remarkable property is that the size of the effect doesn't depend on distance. Ordinary brightness falls off with the square of distance, so distant clusters are hard to detect. This effect depends only on how much hot gas the light passed through, so a cluster at enormous distance produces the same imprint as a nearby one, which makes it ideal for finding clusters anywhere, including behind the dust of our own galaxy, since microwaves pass through it unimpeded. Surveys using this method have catalogued thousands of clusters, and it's one of the routes now filling in the obscured regions of the sky. Since so much of tonight has been about obscuration, let's spend a chapter on how astronomers handle it quantitatively. To recover a galaxy's true brightness from behind the dust, you need to know how much dust is along that line of sight. That requires a map. The standard maps were produced in the 1990s, using satellite observations of the infrared emission from the dust itself. Dust absorbs starlight and re-radiates it in the far infrared, so its glow reveals how much is there, and from that, the extinction at any wavelength can be calculated. Those maps are used constantly, by essentially every extragalactic astronomer, to correct measurements for foreground dust. They've been refined several times since. The correction works well at moderate galactic latitudes. Close to the plane it becomes unreliable, because the dust is patchy on small scales, because the relationship between infrared emission and extinction breaks down at high column densities, and because you can't easily separate foreground from background. So the mapping has a boundary, and inside that boundary, the numbers become uncertain rather than wrong. Which is the honest summary of the whole zone of avoidance problem in one detail. The correction exists, it works over most of the region, and it fails precisely where we'd most like it to work. A question worth a chapter. How long has this motion been going on? The flows we measure are the accumulated result of gravity acting over cosmic time. Density variations were tiny in the early universe, and the velocities they produced were correspondingly tiny. As structure grew, the gravitational gradients steepened, and peculiar velocities grew with them. So our motion has been building for most of the universe's history, gradually, as the cosmic web assembled. The growth rate peaked in the era when matter dominated the universe's dynamics and has been slowing since dark energy took over about 5 billion years ago, because the accelerating expansion suppresses further growth of structure. Which means our 630 kilometers per second is close to the maximum it will ever be. It grew for billions of years, and it's now near a plateau, and it will begin to decline as the structures producing it are pulled apart. There's something rather nice about that. We happen to be alive during the era when the flow is at its strongest, not because anything special is happening, but because it took 10 billion years to build and will take tens of billions to fade. The current is at full strength, and it will be for a while, and then it will slacken and stop. Let's spend a chapter simply on the counting, because the scale is worth stating. Laniakea contains roughly 100,000 large galaxies. Each of those contains, on average, something like 100 billion stars. So the structure we're a part of contains something like 10 to the 16th stars. Its mass is around 10 to the 17th solar masses, most of it dark matter. Its diameter is 520 million light-years. Light crossing it takes 500 million years, longer than complex animal life has existed on Earth. And every one of those 100,000 galaxies is drifting at a few hundred kilometers per second toward a common region. A coherent motion involving 10 to the 16th stars, organized by nothing but gravity acting over 10 billion years. Beyond it, the Shapley concentration contains its own tens of thousands of galaxies, and Laniakea appears to be drifting toward that. There's no way to hold those numbers meaningfully. What I'd suggest instead is holding the coherence, that this many objects, spread across this much space, are all moving the same way. And the reason is a slight imbalance in the distribution of matter laid down in the first fraction of the first second. None of this would have been possible without people patiently listing things, and it's worth a chapter on that unglamorous work. Charles Messier, in the 1770s, catalogued about 100 fuzzy objects, not because he cared about them, but because he hunted comets and wanted a list of things that weren't comets. In the 19th century, that grew into the new general catalogue, listing thousands of nebulae and clusters compiled from visual observations. Objects in it are still referred to by their NGC numbers today. Then Fritz Zwicky, whose work on dark matter and neutron stars we've discussed on other nights, spent decades compiling a catalogue of galaxies and clusters, published in 6 volumes through the 1960s, containing tens of thousands of objects measured from photographic plates. And George Abel, working from the Palomar Sky Survey plates in the 1950s, produced a catalogue of galaxy clusters, identified by eye as concentrations on photographs. It's still used. The Norma Clusters designation, Abel 3627, comes from the southern extension of his work. Those catalogues were built by people examining photographic plates for years, marking positions, estimating magnitudes, recording everything by hand. And every modern result about large-scale structure rests on them. Let's turn it around for a chapter, because the symmetry is worth appreciating. Suppose there were astronomers in a galaxy in the Norma cluster, 200 million light-years away, doing the same work we do. They would measure their own motion relative to the microwave background, and they'd find something, a peculiar velocity of their own, pointing toward whatever dominates their neighborhood, most likely toward the Shapley concentration. They would not see themselves as sitting at the center of anything. From their vantage point, they'd be an ordinary cluster in an ordinary filament, being pulled by things further out, exactly as we are. And when they looked in our direction, they'd see a modest region, a couple of large spirals and their companions, in a fairly ordinary group, at the outer edge of the same basin. Nothing to remark on. There's no center to any of this. The great attractor is the low point of our catchment, defined by which way things flow, not by any intrinsic property. From a different position, a different region would be the destination. We're on a slope, and slopes are relative, and everyone is on one. A brief chapter on the practical question, since people wonder. 220 million light-years is not a distance that means anything in terms of travel. Our fastest spacecraft, at around 70 kilometers per second, would take about 1 trillion years, 70 times the current age of the universe. Even at the speed of light, it would take 220 million years, which is longer than the time since the first dinosaurs. And, as we've discussed, the destination is receding faster than anything could approach it. The expansion at that distance exceeds any conceivable travel speed short of light, and the gap is widening. So it's unreachable in the strongest sense, not merely far, but permanently separating. The same applies to essentially everything beyond our local group. Of the 2 trillion galaxies in the observable universe, the overwhelming majority are already beyond any possible contact, even at light speed. The Great Attractor is something to know about rather than something to go to. Permanently a direction rather than a destination. Let's take a chapter on how these motions have changed over time, because it puts the present in context. Early in the universe's history, matter was distributed almost uniformly, and peculiar velocities were tiny, a few kilometers per second, perhaps less. As gravity amplified the density variations, the gradient steepened and the velocities grew. By the time galaxies were forming, flows of tens or hundreds of kilometers per second were developing. Structure formation peaked in the middle of cosmic history, when the universe was a few billion years old. The era when mergers were common, star formation was at its maximum, and clusters were assembling rapidly. Since then, the growth has slowed, and for the last 5 billion years, dark energy has been actively suppressing it. Regions that would once have collapsed together are now being separated. So the cosmic web has essentially reached its final configuration. The flows are still running, we're still measuring 630 kilometers per second, but they represent the last stages of a process that has already peaked. A chapter on the cultural side, because the Great Attractor has a public presence unusual for a cosmological topic. Part of it is the name. Alan Dressler chose well. 2 ordinary words, combining into something that sounds enormous and slightly ominous, and which is easy to remember. Part of it is the hiddenness, a thing we can't see behind our own galaxy, pulling us. That structure is irresistible as a story, and it maps onto very old narrative shapes. And part of it is timing. The discovery arrived in the late 80s, when popular science publishing was expanding, and when large-scale structure was making news generally. The result is that the Great Attractor appears constantly in documentaries and videos, usually described as mysterious, often with dramatic music, and frequently with the 1988 numbers presented as current. I don't think that's harmful exactly. It brings people to a genuinely interesting piece of astronomy. But the widely known version of this story is 35 years out of date, and rather more dramatic than the evidence supports, which is why tonight's version has been so insistent on the ordinariness. The truth is, a good story too. It's just a quieter one, about surveys and dust corrections, and the slow closing of an accounting gap. One more piece of physics before the recap. Since dark matter dominates everything we've discussed, about 85% of the matter in the universe is dark, detectable only through gravity, not through any interaction with light. It's what makes galaxies rotate as they do, what holds clusters together, and what provides most of the gravity in the flows. So when we say the Great Attractor region contains a large concentration of mass, most of that mass is dark matter. The galaxies we can see, and even the hot gas that outweighs them, are a minority component tracing a much larger invisible structure. That's why peculiar velocities are so valuable. Light-based surveys map the visible tracers. Velocity measurements map the gravity, which responds to everything. And the two agree reasonably well. The mass distribution inferred from flows matches the distribution inferred from galaxy counts, once you assume a sensible relationship between where galaxies are and where mass is. That agreement is a quiet but significant success for the standard picture. So the thing pulling us is mostly something nobody has ever detected in a laboratory, and we know where it is and roughly how much of it there is because of how the galaxies move. Since the dust has been the villain all evening, let's spend a chapter on what it actually is and where it came from. Interstellar dust grains are tiny, typically smaller than a wavelength of visible light, some as small as large molecules. They're made of silicates, of carbon in various forms, and of iron-bearing compounds, often with icy mantles in cold regions. And they were all made in stars. Grains condense in the cooling outflows of dying stars, in the winds of red giants shedding their outer layers, and in the expanding debris of supernovae, where the temperature drops through the range where solids can form. So the dust that blocks our view is the residue of previous generations of stars, scattered through the disk, accumulated over billions of years. It concentrates in the disk for the same reason the gas does. It settles toward the plane, because material orbiting in a rotating system loses vertical motion through collisions and ends up flattened. Which means the obstruction is a direct consequence of our own galaxy's history. If we lived in an elliptical galaxy, gas poor, dust poor, with no disk, the whole sky would be available, and the Great Attractor would have been catalogued as an ordinary supercluster decades before anyone thought it was mysterious. We are, in a small way, hidden from part of the universe by the exhaust of stars that died before the sun was born. That flattening deserves a chapter because it explains the shape of the problem. A galaxy's gas collapses into a disk because of angular momentum. The material can lose energy by radiating heat away when clouds collide, but it can't easily lose rotation, so it settles toward the plane perpendicular to the net rotation and stays spread out within that plane. The result is remarkably thin. The Milky Way's disk is about 100,000 light-years across and only a few thousand thick. Proportionally thinner than a sheet of paper is compared to its width. The gas and dust are thinner still, concentrated in a layer, perhaps a few hundred light-years thick, with the young stars forming within it. Which means the obscuring band on our sky is narrow. Move a few degrees away from the plane, and the extinction drops rapidly. Move 10 or 15 degrees, and it's usually manageable. That's why the zone of avoidance is a stripe rather than a hemisphere, and why the problem is severe but bounded. And it's also why the innermost few degrees remain difficult. That's where you're looking along the length of the thin layer rather than across it, so the amount of material in the line of sight is greatest. A chapter on how these maps are drawn, because knowing the convention makes them much easier to picture. Astronomers usually plot the whole sky in galactic coordinates, a system where the equator of the map is the plane of the Milky Way, and the center of the map is the direction of the galactic center. That's convenient for this subject, because in that system, the zone of avoidance is a horizontal band across the middle of the map, symmetric and easy to identify. The map itself is usually an oval, produced by a projection that preserves areas, so that a region's size on the map matches its true share of the sky, even though shapes get distorted near the edges. On such a map, the microwave dipole appears as a smooth gradient, one side warm, the other cool, with the transition running across the middle. The Great Attractor direction sits toward the left of center and slightly below the equator, close enough to the band to be obscured. And the galaxy distributions plotted the same way show the empty stripe immediately. It's a striking image once you know to look for it. A map of the universe with a bandage across its middle, exactly where our own galaxy sits. Let's return to the surveys that first pierced the band, because the infrared work was transformative. In 1983, a satellite surveyed almost the entire sky in the far infrared for the first time. It was a joint project between 3 countries. It operated for 10 months until its coolant ran out, and it changed several fields at once. Among its results were the dust maps that made extinction corrections possible, and the discovery of large numbers of galaxies that shine mainly in infrared, including many in obscured regions. Then, in the late 1990s and early 2000s, an all-sky survey in the near-infrared, using twin telescopes in Arizona and Chile, catalogued 500 million objects. Because near-infrared extinction is roughly 1/10 of the optical, it recovered galaxies from regions where optical surveys saw nothing. That catalogue became the basis for a redshift survey of tens of thousands of the brightest infrared galaxies across the whole sky, including through much of the Zone of Avoidance. And from that survey, the gravitational pull on us could be calculated directly by summing the contributions of all the catalogued galaxies. The result agreed reasonably well with the motion measured from the microwave dipole, which was an important consistency check. So two entirely independent approaches, the temperature pattern of the oldest light and the summed gravity of catalogued galaxies, give compatible answers. That agreement is a large part of why nobody thinks anything exotic is going on. Since distances underpin everything, let's spend a chapter on the methods we haven't covered. The tip of the red giant branch is one of the most reliable. Old stars in a galaxy reach a maximum brightness at a well-defined point in their evolution, producing a sharp edge in the distribution of stellar brightnesses. That edge occurs at a known luminosity, so finding it gives a distance. It works for galaxies close enough to resolve individual stars. Surface brightness fluctuations exploit a statistical effect. A nearby galaxy has fewer stars per pixel, so the pixel-to-pixel variation in brightness is larger. A distant one is smoother. Measuring that graininess gives a distance, and it works well for smooth elliptical galaxies. Type Ia supernovae are the long-range method. Because these explosions occur at a fixed mass threshold, they reach nearly the same peak brightness, and with a correction based on how quickly they fade, the scatter tightens further. They're visible across enormous distances, so they extend the reach of peculiar velocity surveys far beyond the other methods. Each has different systematic errors, and each must be calibrated against the others. The result is a ladder, nearby methods calibrating more distant ones, and every rung introduces uncertainty, which is why the field puts so much effort into cross-checks, and why distances to individual galaxies remain uncertain at the level that makes peculiar velocity work so demanding. Let's return to constrained simulations, because they've become one of the main tools for answering tonight's question. The approach starts from the observed distribution and motions of galaxies, works backwards to infer what initial conditions would have produced them, and then runs those conditions forward with full physics. The output is a simulated universe containing our actual neighborhood, a Virgo cluster in the right place, a local group with two large spirals, a great attractor region, a local void. Several such projects have run over the past 2 decades, and the most recent produce local universes that reproduce the observed flow field closely, which is itself a test of the underlying cosmology, because a wrong model wouldn't fit. They're used for questions the observations can't answer directly. How much mass is hidden in the obscured region? What will the flows do over the next billions of years? How did our particular configuration assemble? And they can be used to estimate uncertainties honestly, by running many realizations consistent with the data and seeing how much the answers vary. So part of the modern answer to what's behind the Milky Way comes from a computer model constrained to match everything we can see, and asked what must be in the part we can't. Let's spend a chapter on what's happening at the telescopes tonight, because several projects will sharpen this picture considerably. A large spectroscopic instrument in Arizona, with 5,000 robotically positioned optical fibers, is surveying tens of millions of galaxies. Alongside its main cosmological goals, it includes a program dedicated to peculiar velocities, measuring distances to a large sample of nearby galaxies using the fundamental plane and Tully-Fisher methods. That single program will produce more peculiar velocity measurements than all previous surveys combined, which should reduce the uncertainties in the local flow field substantially. A radio survey in Western Australia is mapping neutral hydrogen across the southern sky with a wide field array, detecting hundreds of thousands of galaxies, including many behind the galactic plane, and providing rotation widths for Tully-Fisher distances. In the longer term, a very large radio array under construction across Australia and South Africa will go deeper still, and an extremely large optical telescope in Chile will contribute supernova distances in enormous numbers. Between them, the flow field over a region several hundred million light-years across, should be mapped with several times the current precision within a decade or two, which means the accounting, how much of our motion comes from where, should close much more convincingly than it does tonight. A short chapter on the stakes, because there's a version of this where the answer becomes genuinely interesting. If the improved measurements confirm that bulk flows are larger than the standard model predicts, that would be a real problem, because the model's predictions for flow amplitudes follow directly from the amount of clustering it predicts. Possible resolutions would include more power in the initial fluctuations on very large scales, or a modification to how structure grows, or something about dark energy behaving differently than assumed. Similarly, if the dipole seen in distant quasar catalogues holds up as significantly larger than the microwave dipole, that would suggest either that our motion isn't the whole explanation for the microwave dipole, or that the distant universe isn't as uniform as the cosmological principle requires. Either would be significant, and both are being examined carefully. The most likely outcome, based on the history of this field, is that improved data and better systematics handling bring things into line. That's what happened with the very large flow claims of the past. But the possibility that they don't is precisely why these measurements are worth making. A discrepancy that survives better data is how new physics announces itself, and this is one of the few places currently offering one. Let's take a reflective chapter, because there's something worth noticing about the shape of this problem. For most of the history of extragalactic astronomy, 20% of the sky was simply unavailable. Not difficult, unavailable. And it wasn't a random 20%. It was a continuous band that could bisect any structure. Imagine trying to map a landscape with a permanent wall across the middle of your view, and having to infer what's behind it from how water flows around it. That's essentially what was done. The gravitational effect of the hidden region was measured through the motion of everything visible, and the mass responsible was reconstructed from those motions. And when the region was eventually surveyed by other means, radio, infrared, X-ray, the structures found were broadly where the flow analysis said they should be. That's a rather satisfying vindication of an indirect method. The map drawn from inference matched the map drawn later from direct observation. It's also a reminder that observational limits shape which questions look mysterious. The Great Attractor was a puzzle because of where it happened to sit relative to us, an accident of our own position, not a property of the universe. Let's finish the survey with the story of the Norma cluster, because it's a good illustration of the whole problem. It was catalogued in the 1950s from photographic plates as one of thousands of concentrations of galaxies noted in the Southern Sky Survey. Nothing marked it out. The reason is extinction. At its position, close to the galactic plane, the dust dims everything behind it by a factor of several, enough that a rich cluster looks like a modest one, and a modest one looks like nothing. So for decades it sat in the catalogues, underestimated, while astronomers looked elsewhere. Then X-ray observations in the 1990s revealed an enormous quantity of hot gas, a signature that can't be dimmed by dust, indicating a cluster far more massive than its optical appearance suggested. Follow-up work confirmed it. Hundreds of member galaxies, a mass around 10 to the 15th solar masses, comparable to the Coma cluster, and sitting close to the focus of the local flow. So the nearest thing to a physical object at the heart of the Great Attractor is a cluster that had been catalogued 40 years before anyone realized what it was, hidden not by distance or subtlety, but by a screen of dust in the foreground. One more piece of our local geography before the recap, because it's an odd and rather charming detail. Our local group doesn't sit at random within the larger structure. It belongs to a flattened arrangement of nearby galaxies, sometimes called the local sheet, a plane of galaxies extending across several tens of millions of light-years, only a few million light-years thick. We're within it, and so are most of the galaxies out to about 20 million light-years. The plane is tilted relative to our own galaxy's disk, and it lies roughly along the boundary of the local void. The interpretation is that the sheet is a wall of the void, material that drained out of the emptiness and piled up along its edge, flattened by the process, as simulations of void evolution predict. Which means our neighborhood's shape is a consequence of the emptiness next door. We live on the shore of a large hole, in the sediment that collected there. Measurements suggest the sheet is being pushed away from the void at a couple of 100 kilometers per second, which contributes to the flow we've been discussing all night. So even our immediate arrangement, which galaxies are nearby and how they're distributed, reflects the same landscape of density that produces the great motion. The local and the large scale are the same story at different zoom levels. A final practical chapter, because tonight's measurements feed into one of the biggest open questions in cosmology. The expansion rate of the universe is measured two ways, as we've discussed on other nights. Locally, by measuring distances and redshifts of nearby galaxies, and indirectly, by fitting a model to the oldest light. The two disagree by about 10%, and the disagreement has hardened as measurements improved. Peculiar velocities matter for the local measurement, because a galaxy's redshift includes both expansion and its own motion. If you don't correct for the peculiar velocity, you get the wrong expansion rate. The corrections are made using exactly the flow maps we've been discussing, and they're not negligible. For nearby galaxies, a peculiar velocity of a few hundred kilometers per second can be a substantial fraction of the measured redshift. So one of the questions examined carefully was whether flow corrections could explain the discrepancy, whether we happen to sit in an unusual local region whose motion biases the measurement. The answer, after considerable work, appears to be no. The effect is too small, and the discrepancy persists after correction. But the checking mattered, and it required the flow field to be known well, which is one more reason why measuring what's pulling us has practical consequences beyond curiosity. Let's take stock, gently, before we start winding down. The measurement is secure. Our local group moves at about 630 kilometers per second relative to the frame in which the oldest light is uniform, toward a point in Hydra and Centaurus close to the plane of our own galaxy. The cause is gravity, acting on the uneven distribution of matter across a few 100 million light years. The main contributors identified so far are the Hydra-Centaurus concentration, including the Norma cluster, the much larger Shapley concentration beyond it, and a large underdense region on the opposite side of the sky. The name Great Attractor refers to the nearer concentration, and it was coined when it seemed to be the whole answer. It isn't, and the term now names a region rather than an object. There is no mystery of physics here, only an accounting problem made difficult by our own galaxy sitting in the way. And that problem is being solved steadily by radio, infrared, and X-ray surveys. And the flow will never complete. Dark energy is already pulling these structures apart faster than gravity can gather them. We're drifting toward a destination that recedes. So the honest answer to tonight's question is, we're falling gently down a gradient in the distribution of matter, toward a large concentration of ordinary galaxies behind the dust of our own, in a journey that will never arrive, and that has no effect on anything whatsoever. If you're still awake, let's walk back through it once more, gently, with nothing to follow and nowhere to arrive. It began with a number attached to you, 630 kilometers per second, the motion of our entire galaxy and everything bound to it, on top of the Earth's spin and its orbit, and the Sun's journey around the galaxy. 2.25 million kilometers an hour, felt by nobody ever. And it has a direction toward the southern constellations of Hydra and Centaurus, which is precisely where we cannot look, because our own galaxy's dust lies in the way. For most of the history of astronomy, maps of the galaxies had a blank stripe running across them, and it was named the Zone of Avoidance, and whatever we're falling toward is inside it. We know we're moving because of the oldest light. The microwave background is very slightly warmer on one side of the sky and cooler on the other, a few thousandths of a degree, which is a Doppler shift, and from it our velocity can be read directly. Then, in the 1980s, 7 astronomers spent years measuring distances to hundreds of elliptical galaxies, and found that everything across an enormous region was streaming the same way. They suspected their own error first, and looked for it for a long time, and eventually published. Alan Dressler called the destination the Great Attractor, and the name escaped into the world and never came back. Then the slow business of looking through the dust. Infrared, where the obscuration drops by a factor of 10. Radio, at 21 centimeters, where the dust is simply transparent and hidden galaxies could be counted one by one. And X-rays, which pass through anything and reveal clusters directly by the hot gas between their galaxies. What was found is a real concentration, the Norma cluster, previously catalogued and underestimated, along with Centaurus and Hydra and a wall of galaxies connecting them. A rich complex in the right place that had been substantially hidden by our own galaxy. But not enough to explain everything, so attention moved further out, to the Shapley concentration at 650 million light-years, the largest mass concentration in the nearby universe, noticed on a photographic plate in the 1930s by a man who set it aside. And then, in 2017, the other half of the answer, a great underdense region on the opposite side of the sky, pushing us not with a force, but because everything else pulls and it doesn't. They called it the dipole repeller, and it may contribute as much as the attractors do. So there is no single thing. There's a landscape of density, hills and valleys, hundreds of millions of light-years across, laid down by quantum fluctuations in the first instant, and grown by gravity for 13 billion years. And we are drifting gently down a slope in it. The flow was mapped and named in 2014. Lanier K, Immeasurable Heaven, a catchment 520 million light-years across, containing 100,000 galaxies, all draining toward the same low point. And it will never fill. Dark energy is already pulling it apart faster than gravity can gather it. We're falling toward a destination that is receding, and always will be. Let me leave you with some things to rest your attention on, not to learn, just quiet facts, true right now, while you lie still. Filling this room, arriving from every direction at once, is the light released when the universe became transparent, and it is very slightly warmer on one side of the sky than the other, by a few thousandths of a degree, because we are moving 220 million light-years away, in the direction of Norma. Hundreds of galaxies are orbiting each other in a cluster, whose gas glows at tens of millions of degrees, and whose light reached us tonight after traveling since before the first dinosaurs. 400 million light-years beyond that, dozens more clusters are packed together in the largest concentration of mass in our part of the universe, noticed on a photographic plate in South Africa in the 1930s, and set aside as an oddity for 50 years. On the opposite side of the sky, a vast region of relative emptiness is quietly not pulling on us, which turns out to be half the reason we're moving at all. And in observatories in Australia and South Africa and Chile, and in orbit, telescopes are surveying the band of sky that used to be blank on every map, finding galaxies nobody has ever seen, filling in the last part of the picture. They're doing it tonight, and they'll still be doing it in the morning. So here's where we stop. You've been moving at 630 kilometers per second your entire life, along with everything you've ever seen, and you have never once felt it, and it has never once affected anything. There's nothing pulling at you. There's a slope in the distribution of matter across a few 100 million light-years, and everything on that slope drifts gently downhill, and we are part of everything. And the destination is receding. The flow will slow over the coming billions of years and stop, and our own small group will merge into a single galaxy and sit alone, and none of it requires anything from anyone. Let your breathing get slower. You don't have to make it happen. It's already happening, on its own, the way it has all your life. Let your jaw loosen. Let your hands stay wherever they've fallen. Let the bed take your whole weight. Outside, above the roof, there's a band of stars and dust across the sky, and behind it, hidden and entirely ordinary, a great many galaxies going about their business, 200 million light-years away, having no idea we exist and no effect on your morning. You're lying perfectly still, in the middle of the fastest motion you will ever have, and there's nothing to hold on to, and everything that's holding is holding on its own. Sleep well.